This is on extreme values of functions on closed intervals. So to begin with, your objectives are to be able to find extrema, which is the multiple of like many extremes from graphs, finding the absolute ones on finite closed intervals, finding critical points and local extrema and critical points. Remember, in general, a critical point would be things like a minimum or a maximum. Okay, so why you're studying this is one of the most important applications of the derivative is its use as a tool for finding the optimal or best solution to problems. Optimization problems abound in mathematics, physical science, engineering, business, and economics, and biology and medicine. So I may have mentioned before that one of my nephews was a business major and he took business calculus. Same thing with my son. For example, what are the height and diameter of the cylinder of the largest volume that could be inscribed in a sphere? What are the dimensions of the strongest rectangular wooden beam that could be cut from a cylindrical log of a given diameter? And other questions like, based on production costs and sales revenue, how many items should be made to maximize profit? And how does the trachea or windpipe contract to expel air at a maximum speed during the cough? What is the branching angle at which blood vessels minimize the loss of energy due to friction? So that's general overview of like what it would be used for. In this chapter, we apply derivatives to find extreme values, to determine and analyze the shapes of graphs, and to solve equations numerically. We also introduced the idea of recovering a function from its derivative. The key to many of these is the mean value theorem, which connects the derivative and the average rate of change, or the average change of a function. So here's your formal definition. In college, sometimes they make you memorize formal definitions when you're doing proofs. So here's an example. Like the problem would be define what absolute maximum is. So, and they want it to be word for word, and they want it to be specific. So your definition is let f be a function with domain D, then f has an absolute maximum if you're using the less than or equal to symbol. Okay, so has an absolute maximum value on D at a point C if f of x is less than or equal to f of c for all x in D, and it's an absolute minimum if it's greater than or equal to. So absolute minimum value on D at a point C if f of x is greater than or equal to f of c. Make sure you're paying really close attention to your less than and greater than in case you have a Google form, because some of them will be true and some will be false. So if it's maximum, it's less than or equal to. If it's minimum, it's greater than or equal to. Okay, and that's assuming it goes left to right, like f of x and f of c. So you might want to highlight that or remember that. Maximum and minimum values are called the extreme values. Absolute ones are also called global. So absolute and global mean the same thing. And then here's a theorem. So this is called the extreme value theorem. So if I said write the extreme value theorem word for word. It would be, if f is continuous on a closed interval AB, then f attains both an absolute maximum value capital M and a minimum value little m, or lowercase, in that interval AB that's closed. That is, there are numbers x1 and x2 in that interval AB, with f of x1 equal to the lower one and f of x2 equal to the upper one, and it goes lower the function, the upper, for every other x in AB. That doesn't literally mean every other one, like 1, 3, 5. It means for everything else. Okay? All right, so for number 7, it says your definition, a function f has a local max at a point C within the domain if it's less than or equal to in some open interval containing C, and it's a local minimum if it's greater than or equal to in some open interval. So the main idea is it's local, so it has to be open. Local is open. Whereas absolute is closed. Okay, so I'm just going to say compare to absolute, which is closed. So then number 8, local are also called relative. And then you have a theorem that's the first derivative theorem for local extreme values. If f has a local max or min at some interior point, and if f prime is defined at C, then that f prime of C is 0. So when you do your derivative, it's equal to 0. Your definition is an interior point of the domain where f prime is 0 or undefined is called a critical point. So if it's 0 or undefined, that's a critical point. So say you're going to have a graph, and here's a max. So that's going to be f prime is 0 at that point. And then this one, f prime is 0 at that point. I'll put that for both of them. Okay. And then there's also ones on finding it on a closed interval. What you do is find all the critical points and evaluate them at the critical points and at the endpoints, and take the largest and smallest. Okay, so now let's go through these. So basically the first one says, determine from the given graph whether the function has any absolute values, then explain how your answer is consistent. So look, what you see on this graph is it is an open circle at the max. That's a piecewise function, and because it's an open circle, then it does not have any absolute ones. And then it says explain it, and it's because it's not continuous. Now notice 2 of them say not continuous. And then the other part that's different is this says is a closed interval, and this is not a closed interval. And the reason is because, you know, here would be a parentheses and this would be a parentheses, not brackets. So parentheses were open and the brackets were closed. So not going to be too detailed, but of course, you know, open means not closed. Okay, so there's number one. Number two, here we have another piecewise function, whatever the function is, and this one's open, and so there is no absolute maximum, so that means it has to not be B or D. And now this part says there is no absolute minimum, and this one says it occurs. So this particular spot is the absolute minimum. And if you want to be technical, it has it for you. It occurs at x equal a on that interval AB. So that's what you want. And then explain it. It does not satisfy the criteria. So it may or may not exist. It's not that it must not. It may or may not. Okay, so use your examples on this. On this one, you have an absolute value x minus 2 from a certain interval 0 to 3, and you just want to graph it. It's a V-graph, and it's going right 3. And so that's this one. Now, because it's a less than for both, it has to be open for both. So it's not D. It's like a backwards check mark. Then determine whether it has any absolute extreme values. It does have an absolute minimum here. This is the absolute minimum, but it does not have a maximum because that's an open circle. And then it says explain it. Well, since it is continuous, it may or may not have it. So 2 of these say continuous, 2 of them say not continuous, and it says may or may not attains both. Okay. These are all like tying it to an explanation. So here you have a piecewise function, and it's 2x from -1 to 0, which means it'd be positive slope, which means it can't be this one or this one because of this stuff, because that would have negative slope. And then the next one would have negative slope, which is like that. But the difference is this is -2x minus 1, which tells you your y-intercept equal -1, which is why it's lower. This one has y 0. Okay, and so the maximum would not exist, or they may say may or may not, and then the minimum is right there. There's the absolute minimum at 1, at x equal 1. So your absolute minimum at x equal 1, but it does not have a maximum on the domain. And this is where, again, I said may or may not have, because it's not continuous. So this one says does not attain, and this is may or may not, and that's what you want to look for. Now this one, we have a trig function, -3 sine, and so you know that reflects the x-axis. And so instead of being like this, it's like this. And then you know this has got to go from -3 to 3. Okay, so then you're going to need to find where your value happens. And let's see if it's going down like that. This one's up first, and this one's up first. And what's the difference? The difference is these are open on the end points, and these are closed on the end points. And because we want less than, we want open on the end points. And so then the maximum happens at, let's see, 0, pi halves, pi, which is 2 pi halves. Then here's 3 pi halves. And then there's 2 pi, and then 5 pi halves. And so the minimum happened at pi halves, and the maximum was at 3 pi halves. So let me make that larger, like that. And so that's what we want. The max at 3 pi halves, the min at pi halves. And it was an open interval, and it was continuous, and so it may or may not. So rule out the ones that are not continuous, and this says attains both, and this is may or may not. Now, on one like this, you're done with the explanation part. You just need to graph it. And here's the main thing. Pay attention to your interval. In particular, you're going to want to use your table. So, we have x squared minus 9. Okay. And our interval is from -4 to 3. And so we go to -4. And it has 7. And we go to 3. And it has 0. And then when we look for the symmetry between, like I see -1, -8, I see 0, -9, and I see 1, -8. So that means this is my vertex. In this case, it'd be the minimum. Okay, so on that interval, our biggest y number is 7, and that happens at x equal -4. And then the smallest y happens at 0. Now, if you want to compare it, here's the thing. So if you get rid of your table and we make this like -20, you can actually see that your minimum is 0 to -9 on the graph. So on the graph, 0, -9 is the minimum. Whoops. That's funny. Minimum. In this case, it's both the local and absolute. But if you're looking at the graph, you don't know the highest point. It depends on the interval. And so you can't use the maximum feature unless you're like overthinking it. Like if you literally change your window from -4 to 3, then you can say, oh, well, what was it right here? Well, if that's 6 2/3, then that's 7. So that's the only way you could look at it that way on the graph. I prefer using the table. I mean, that's my preferential method. Otherwise, set your window, but I don't like that as much. I mean, do whatever you want though. Okay, and so then that would be the D graph because it's like that and it's what we want. So this would be the point, -4, 7. This would be the point, 0, -9. And what's that point? The point is 3, 0. Because that's what we needed in our table. 3, 0. Okay. All right. So now we have another one. Now this time we're going from 0.2 to 2. So first let's put the graph in. This is going to be a closed interval. So in general, it's going to look like that. Excuse me. But we want from around 0 to 2. And so we know it's around like that. But I need to make this lower, like maybe -20. Maybe more than that. When I compare these, this one actually says -80, and this one says -16. But I know it's going to be the -80 based on what we see. So if I go -80, then it looks like that. Okay, so there's the correct graph. Now, for your table part, this might be a little bit tricky. Not really. Okay, so this is going to be 2, -0.75, or you could think 2, -3/4. So for your table, 2, -0.75 or 2, -3/4. So that's the maximum because it's the highest. And so that's what we want here. And now for the minimum, we have to basically go to the start of the interval. Now you can't go lower than that, and this is like increasing throughout. This function is increasing throughout. So the lowest is at the beginning endpoint. Let me just say at the first endpoint. And the highest is at the second endpoint. So in other words, it's going to be from 0.2 to 2. So 0.2 for x to x equal 2. Now, how do we get that y value? You could probably just put -3 over 0.2 squared. Otherwise, look in your table. But your table's going to be counting by ones. And so it's probably easier if you just calculate it. -3 divided by 0.2 squared is -75. And if you wanted to, -3 divided by 2 squared is -3 over 4, which is what we said earlier right there. Okay, so that's how that works. Now on this one we have the cube root of x, and we're going from -8 to 1. So why don't we just use our calculator without graphing it? Let's just do the cube root of x. So the cube root of -8 is -2. And the cube root of 1 is 1. And so that means the function is going to go increasing. It's going to be increasing. And it's going to look like that. So to verify that or whatever, it's going to be like nth root. So I'm going to put cube root of x. So there it is. That is also like the one kind of like my ring, you know, it goes like that. So there we go. So the maximum is at 1, 1, and the minimum is at -8, -2. Okay. Now on this one, we're reflecting across the x-axis, and we have a square root function, and we're going from -1 to 0. So let's check our endpoints. So when I go back to this, we go negative square root 1 minus. Okay, notice we have a -1 and we're supposed to square it, so you got to put it in parentheses. So -1 squared. When we do that, we get 0. And then for the other endpoint, it's just negative square root of 1. So that's just -1. Now, remember what I said earlier, it reflects. You might want to graph it just to understand it. Negative square root 1 minus x squared. That means it's like the little semicircle. It's like a little smiley face. But all we care about is from -1 to 0. And so all we care about is that. And so that means that the left is the max and the right is the min. And so the max was the left, which was -1, 0. So they say the value is 0, which happens at -1, and the minimum is basically 0, -1. The y value is -1, and the x value is 0. Okay, I have just a couple more of these. On this one, you're doing x to the 5/3, and you're going from -1 to 8. So you're going to want to do -1 up arrow 5/3, and you get -1. And on 8, you get 32. And then you can say, well, -1 is low, 32 is high, which makes the low one the minimum and the high one the maximum. So the y answer is 32, and that happens at 8. The low one is at -1, -1. Again, these are the y answers. This is the x, the y, the x. Okay, now this one's talking about the critical points. And so we want to know where the minimum or maximum happens. Since it's positive x squared, it's going to be a minimum. If it were negative x squared, it'd be a maximum. So what we want to do is graph it. X squared minus 14x plus 9. Okay, well, from the equation, it's squared, but from the graph, it looks linear. That means we're not at a good window. So you're probably going to want to zoom out. I don't know how much. Now I can tell. Like that. Okay, there's the minimum. Now, because it's a minimum, I go to Analyze Graph and then go to Minimum and trap it between here and here. Now, in the calculator, it says 6 point, basically 9 repeat, which will make 7. Ignore this garbage with the 21746. That's going to be 7. So we think of 7 comma -40. So your answer is 7 because they want the x. And on this one, they want your critical points. So let's graph it. They don't tell you a certain interval, so you have to look carefully. 2x parentheses 4 minus x to the third. And the third goes outside. Now, before I press enter, I'm anticipating it may give me an error. The error would be that there's no time sign listed between the x and the parentheses. Sometimes it doesn't like that. So let's see. Yeah, it doesn't like that. And now I did all this weird stuff. So when you're graphing it, you got to make sure that you're typing it right. Like 2x times parentheses 4 minus x, and then up arrow 3. So now it actually shows it. So I would say 2x times parentheses 4 minus x to the third. If you don't have it, it's a cannot accept change error. You're too structured. You can't accept change. Okay, so what we need to look at is the maximum minimum. So let's zoom out. Can we find it up here? Okay, found it. Go to your maximum between here and here. That's at 1 comma 54. So the max is at 1 comma 54. And then what happens down here? Okay, my minimum didn't do right because I was zoomed out weird. Let's go back to the table. At 4 at 0. And at 1 it was 54. Now, let's think about what we did before in the notes. In the notes, we talked about the derivative having to be equal to 0. So let's work through this, think through it. Let's do it one more time. 2x times parentheses 4 minus x. Oh, it was to the third power, right? Okay. So what happened right there? That's a 0 the graph. And that's at 4, 0. So it's kind of like an inflection point. And so that's what we needed. An x-intercept, which here was the inflection point, which is basically where it went from here to there. So like where it goes, like where it changes concavity, where it changes concavity. Okay, now we could have also done the derivative. It would have used the product rule. Could have done that if we wanted to. You know what? I'm going to do that on this one, but not that one, because this one you'd need the product rule on the derivative, and so I didn't feel like doing that right now. On this one I'll do it. 2x squared plus 4x to the negative 1. So f prime would be 4x minus 4x to the negative 2. So what we do then is set that equal to 0. And so then we'd have 4x, and move this one over, equal to 4x to the negative 2. So basically, when you're working through this, you would divide out your 4's, and x equal x negative 2, well, that would look like x equal 1 over x squared. The only time that's even possible is if it only happens if x equal 1. Because you'd have 1 equal 1 over 1 squared. So that's why it works. Now, if you didn't like the derivative method, okay, this is what I call the derivative method. If you didn't like the derivative method, you could have graphed it. Two x squared plus 4 over x. And so you can kind of tell something happened right there. You might have to zoom out, and then you can see something happened. So if you graph it, it looks a little unique. It goes down, and then it has a little thing like that. And so this spot is a minimum. And so if we go to minimum, from here to here, we get 1,6. And so x equal 1 is your answer. Okay? All right, 2 more. So now on this one, the derivative, well, let's just do f of x first. We have x squared minus 108 square root of x. Let's call that x squared minus 108 x to the half. So that's f of x. Now for f prime of x, that'd be 2x minus, remember how to do this? You have your 108, you have to keep there. You bring your half in front, keep x, and then you have to lower by whole numbers, so this is negative a half. So that means it would be 2x minus, that turns out to be 54, x to the negative a half. And you could think of that as 2x minus 54 over the square root of x. If we set that equal to 0, then that'd be 2x equal to 54 over square root of x. This one would probably be a little more complicated if I do the math. We would want to multiply by square root of x over square root of x. So we get 2x equal 54 square root of x over x. You'd want to multiply by x to get your rid of your denominator. And then you'd have 2x squared minus 54 square root of x equal to 0. Then you'd want to factor out, and this is getting to be a long problem if you do it this way. You may not want to do it that way. I'm just going to say keep going. Let's just try graphing this one, because this one was not as easy, like with the derivative. So x squared minus 108 square root of x, well, it just looks like that. Now, if we look in our table, we have some pretty big numbers. They're getting smaller and smaller here. Okay, it kind of centers around 9 comma 2 negative 243. So if you look in your table, we'd say negative 8 with, wait, that's positive 8. 8 with negative 241.47. 9 has negative 243. And 10 has negative 241.52. And so you can kind of see some symmetry there. And so this is going to be your answer. Okay. So just base it on your y values being symmetrical. It's not completely symmetrical, but it's pretty close, right? Because this is negative 241.47 and this is negative 241.52. So they're only like 0.05 apart. And so this is going to be the one. Now, for your last problem, this one we probably could just get your derivative. 3x squared plus 12x minus 180. Set that equal to 0. This is when you could do your factoring. X squared plus 4x minus 60, right? Divide by 3. And if we factor that, we'd need x plus 10 and x minus 6. Because based on this, we need the bigger one, or bigger term, positive. And if we have a negative 60, one has to be positive, one has to be negative. Now, you can set that equal to 0, so then your answer is negative 10 and 6. Okay, so there you go. That's how you do the problems. Hope that helps. Bye.